Yes. All right, everyone. So we're gonna go ahead and get started. I'm gonna start off with introductions. So I'm Arsh, pronouns he, him. I'm a fourth year computer science major, and I've been with ACM since my freshman year in different capacities. But today and starting this quarter, we have a new initiative, ACM Quantum, which focuses on bringing this difficult to understand technology and an upcoming technology to beginners in a very friendly way in which you can pick up the main concepts. And that is what we aim for. We want you guys to build intuition about what quantum computing is. Okay. So our vision is to focus on intuition and visual learning. We're going to break down some core concepts into simple pieces for you guys to pick up. Along the course, we're going to have some guided projects and worked out examples in the sense that you're going to work on something tangible and see where quantum computing shines. Um, we also embrace feedback and constructive criticism. So we'll be sending out some feedback forms for you guys to tell us how we did in each of our workshops. And lastly, we have the important point. So encouraging students to explore quantum computing. How many of you have heard this term quantum computing? Just a show of hands. Okay, almost everyone in this room. And how many of you guys have an idea of what it is? Okay, so got it. So yes, our main goal is to help people who have just heard this term but really understand what it is. So let's move on. So this is our amazing team. We've been working really hard to bring this initiative together and like build this whole material and advertising, etc. So let's hope you guys have a great time this quarter. So this quarter, we're offering our first track, which is the beginner's track. This is our very first offering, so it will be quite basic in terms of what quantum computing is, where does it stem from, what are its advantages, disadvantages, some core algorithms, implementations, and why you should pursue it. All right. So our agenda for this quarter, covering the first half. All right, come on in, guys. We just got started. Um, the first half will cover the basics. So lecture one, which is today, will cover the introduction and the motivation for quantum computing. Lecture two covers the foundational math that is really needed to understand how this technology works. Lecture three dives deeper into mathematics and some gates and how these gates function. Lecture four, we have the quantum circuit model. The second half of the course really gets into the details of algorithms and looking into the future of where this technology is headed. Lecture five, we have introduction to some core quantum algorithms that many of you would have heard of. We cover Grover's algorithm in lecture six, and lecture seven, we leave you guys off with the scope of this technology. So expected math skills. Just a side note, quantum computing at its very core is an abstraction of some computer science fundamentals. Then we have linear algebra and complex numbers. So we're gonna hope you guys have some knowledge of these. So basic matrix properties, vector properties, some summations, and complex number representations. So before I move forward, I would want to know if any of you don't know these terms. That is completely fine because we're gonna break it down in the next lecture as well. Okay, perfect. So we have a good foundation here. With that, I'm gonna hand it off to Ian to kick us off with our first lecture. Before we start with the lecture, does anyone have any questions about logistics, for example? All right, Ian, you're good.
All
Please
right.
introduce yourself first.
Thank you, Arsh, for that wonderful introduction. My name is Ian Kwan. I'm a third year material science major, just with a massive interest in quantum computing, he, him pronouns, and I will be your speaker for today. All right. There's been a lot of hype surrounding quantum computing recently. It seems like there's like a new article or paper being published pretty much every single day with titles like this. Quantum Leap. Google claims its new quantum computer provides evidence that we live in a multiverse. And teleportation achieved between quantum computers in a world first. These are some pretty crazy headlines, and you might be thinking, is any of this even true?
All right, I'm gonna stop there. Let's see. Did we share the screen before we record it? I
Oh.
mean,
Wait, that's a good point.
yeah, because I don't want to. Okay, yeah. See. One sec. Perfect. Mhm.
That's a good catch, yeah. All right. Anyways, our goal for today is to address these uncertainties and first summarize what is and isn't overblown about quantum computing. Next, I plan to explain what quantum computing actually is and what it is actually capable of. Then I will give you my personal opinion on why I think quantum computing is valuable and why you guys should pursue it. And finally, we will present what is being done in the field today. Busting quantum computing myths and misconceptions. Quantum computing will be able to solve every single problem. This is false. Quantum computing, unfortunately, isn't some sort of holy grail of computing, as much as I wish it was. It's actually only good for solving a limited number of specific problems. It just so happens that some of these problems are really, really important. Quantum computing will replace classical computers. This is false. Quantum computing and classical computing are two separate regimes, actually. While it is true, you could theoretically do everything you can do with a classical computer on a quantum computer, both regimes have their own unique strengths and weaknesses. A similar comparison I could give you would be boats versus cars. With cars, you can drive around, get from point A to point B, but if you need to cross like a body of water, a boat is much more suited for that task. However, even though a boat is better at crossing bodies of water, it'd be impractical to just replace cars outright and drive through the street with like on a yacht or something. In a similar way, there are a lot of problems that are actually pretty impractical to solve with quantum computers. Like you can't attach like a quantum computer to your RTX 4080 and expect to run 8K graphics at like 200 FPS. Like quantum computing will break all public key encryption and all my private information is screwed. This is actually true, kind of. There is an algorithm called Shor's algorithm that makes it very, very easy to factor large integers. This is significant because it breaks RSA encryption. RSA encryption is a form of public key encryption that relies upon the fact that it is hard to factor large integers. However, if we have Shor's algorithm to make that very, very easy, it's like it might as well not be there, you know? However, a caveat is that in order to actually run Shor's algorithm, we would need to first greatly increase the size of our quantum computers. Currently, our quantum computers have anywhere between 100 to 1,000 qubits, and to actually run Shor's algorithm, we need roughly 20 million. But unfortunately, there are some very bad, like clever people out there who are actually storing online data that is encrypted to take advantage of it when we actually get working quantum computers. What is quantum computing and what can it actually do? Before we study qubits and quantum computing, I would first like to review classical bits. What is a classical bit and how do they work? Physically, a classical bit is a small piece of semiconducting material called a transistor that can toggle between stopping the flow of electrons or letting them pass. In order to use bits as objects of binary logic, we apply voltage to a transistor and measure the resulting current. After measuring the current, we use some pre-decided threshold to determine if a signal represents a 1 or a 0. For instance, let's say that we decide the threshold to be 1 amp. If we apply voltage and measure the current to be above 1 amp, the bit represents a 1, and if it is below 1 amp, it counts as a 0. In order to start thinking about bits quantumly, we need to first abstract classical ones and zeros to column vectors, i.e., we need to think of the 0 as the 1, 0 column vector on the left, and we need to think of 1 as a 0, 1 column vector on the right. In this abstraction, think of a general bit as the sum of these two basis vectors, each multiplied by a special coefficient called an amplitude. I know I haven't really gone into amplitudes. I'll explain it in a bit.
Before you move on, so Ian and I have been using this term classical computers. Is anyone confused what a classical computer is? Okay, just to clarify, it is just like a machine that's sitting right in front of you that computes based on zeros and ones, which are binaries, right?
All right. Gosh. In order to start thinking about bits quantumly, before we move on, I would like to first quickly discuss what it means to measure a bit, because it is important to develop an understanding of what an amplitude is. In general, measuring a bit means performing some process to check what that bit holds. For instance, for classical bits, measuring a bit would correspond to applying a voltage and reading out the output. One important thing about measuring classical bits is that the act of measuring a bit does not change the bit's value. For example, if a bit starts out with the value 0, you can measure it anywhere between 1 and an infinite number of times, and each time you measure it, it'll always measure 0 and be in the 0 state as long as you do not do something to directly change the value to 1, like applying a NOT gate. Anyways, going back to amplitudes, what exactly is an amplitude? A kind of oversimplified but quite effective definition of an amplitude is that it is the square root of the probability of measuring the state it is assigned to. An important property of amplitudes is that the sum of the squares of all amplitudes must add up to 1. Why is this? Because, as I just stated before, the square of amplitudes are probabilities, and the sum of all the probabilities of all outcomes must add up to exactly 1. Oh, by the way, if you guys have any questions at any time, feel free to just stop me. I'll be happy to answer you. For classical bits, there are actually two distinct cases, two different ways to assign amplitudes. The first case on the left is where the amplitudes for the 1, 0 column vector or the 0 state is 1, and the amplitude for the 0, 1 column vector or 1 state is 0. This corresponds to when the bit is 0, because obviously when the bit is 0, the probability of measuring it in the 0 state is 1 squared equals 1, or 100%. And the probability of it being in the 1 state is 0. The second case on the right is where the amplitude for the 0 state is now 0, and the amplitude for the 1 state is now 1. Likewise, this corresponds to the case when the bit is 1, because obviously the probability of it being in the 1 state is 100%, and the probability of it being in the 0 state is 0. Now we finally get to talk about quantum bits, or qubits. In this abstraction we have constructed, a qubit is almost the exact same as a regular bit, except for one small caveat. While the amplitudes in classical bits are locked in the two special cases we have just discussed, the amplitudes of quantum bits can take on the value of any complex number with normalization. One thing I want you guys to be thinking about is for qubits, the probability is a probability for of measuring a state still amplitude squared? The answer is no. Why? because the square of complex numbers can be negative, and obviously you can have negative probabilities. This is kind of a spoiler for the next lecture, so I won't delve too deep into it. But in order to find the probability of measuring a state for qubits, you now have to multiply each amplitude by the complex conjugate, because this will guarantee it'll be a positive number. Anyways, the fact that qubits can take on complex amplitudes has some pretty interesting consequences. The first of these consequences is that, unlike classical bits, qubits don't have to be 100% 0 or 100% 1. Of course, they can still take these values, but now they can also be in a superposition of these states. So what is a superposition exactly? Well, a qubit in superposition means that it can exist in multiple states at the same time. More accurately, when you measure a qubit in superposition, you may yield both a 0 or a 1 with non-zero probability. For example, let's say I have a qubit in a superposition. I can measure it 5 times in a row and find it all to be 1. However, without doing anything to the qubit itself, I could also measure it another 5 times and somehow find it to be 0. Why is this? Because for a qubit in a superposition, the amplitude for both the 1 state and the 0 state are non-zero. Thus, when you take the probabilities for measuring each state, it will also be non-zero. Anyways, superposition is one of the quantum properties that makes qubits so powerful because the number of qubits you can access simultaneously scales exponentially as you increase the number of qubits. For instance, just like how a single qubit can, in superposition, you can measure both 0 and 1 without doing anything to it, with 2 qubits, you can be in a superposition of all the bit strings of length 2, i.e. the 0, 0 state, the 0, 1 state, the 1, 0 state, and the 1, 1 state. You can see how powerful this is with as little as 300 qubits. Because with 300 qubits, you can create a superposition that contains 2 to the 300 different states. This is a stupidly massive number that is larger than the number of atoms in the universe. Another quantum property that I kind of want to delve into is entanglement. Entanglement is the phenomenon in which 2 or more qubits can become linked in such a way that the outcome of measuring one qubit influences the measurement of the other, no matter how far away they are from each other. For example, let's say I have a pair of qubits entangled in such a way that they measure the same value. One right here in the room with me and the other in the middle of, I don't know, Zimbabwe or something. Okay. Anyways, let's say I measure the qubit in the room with me to be 1. Because the 2 qubits are entangled, somehow by measuring my qubit to be 1, it influences the other qubit in Zimbabwe to also measure 1 when it gets measured. Freaky, right? Okay, I gotta be honest, entanglement is actually more relevant for quantum communication, which is like a whole different field, but it does show up in quantum computing, so I figured I might as well mention it. All right, so how does quantum computing actually work? One idea I want to get across to you guys is that quantum computing is very, very low level. Similar to how we can apply and, or, not, and like XOR gates to like regular classical bits, we can apply quantum gates to qubits and do operations on them. So quantum computing is less like Python and Java and more like C, assembly, machine code, that kind of stuff. You can read out the output after doing a bunch of operations on qubits by doing a measurement, like I said before, which forces all the qubits to become 0 or 1. So what problems is quantum computing actually good for? Quantum computing is good for problems that require high number of compute and parallelism. Some of these problems might be like brute force type problems, like unstructured search, which is the sort of needle in a haystack problem, you know? You have a bunch of different inputs and you go through all the inputs one by one to figure out which input is the one you're looking for. Very, very time consuming on a classic computer. Another such problem would be the traveling salesman problem, which is you have a bunch of cities and that are all connected with different roads of different lengths. What would be the most optimal way to travel between all the cities, you know? And lastly, integer factorization, which I mentioned before. Obviously, the list of problems it's good for goes on and on. Anyways, quantum algorithms are able to solve these problems much more efficiently than a classical computer because they use quantum properties like superposition and entanglement that will allow usually like at least quadratic, but can get up to exponential speed up. Secondly, quantum computing is very, very good for simulating quantum systems. This is actually the original motivation that was proposed by the famous physicist Richard Feynman all the way back in like the 50s or 60s. The reason why is that quantum systems is actually very, very challenging for classical computers to simulate, especially as you try to simulate how they change with time. However, qubits naturally have quantum properties built in, right? So they don't have to do the extra calculations that classical computers have to do, and they end up getting an exponential speed up over classical computers. On the right over here is a physics equation called a time-dependent Schrodinger equation, which is an example of the type of things you want to simulate on a quantum computer. And here is the part where I try to convince you guys to study quantum computing. All right, the first reason why I think you guys should study quantum computing is because I feel like it introduces a unique and elegant way to solve problems. When you solve problems using quantum computing, you train your brain to analyze problems with different goals in mind compared to if you're trying to solve them classically, right? I feel like this gives you a fresh perspective that a classical computer scientist could not be able to come up with. So you have like extra tools in the toolbox to approach problems. Secondly, I feel like the notation, the operations, like all the equations and stuff you have to do, the theory behind it is very, very elegant and self-contained. You've all had like those like lectures in class, professors, they pop up some meaningless equation on the board and you're like, what the heck does this even mean, right? Quantum computing is not like that. It's built upon linear algebra, and I feel like it's very, very easy to see how one property / one effect comes about, and it's extremely self-contained. Secondly, quantum computing tackles some very, very important problems. Obviously, like I mentioned before, Shor's algorithm speeds up integer factorization, which pretty much screws over all like RSA-based encryption. Secondly, currently the most efficient solutions for NP-hard problems, to those of you that have taken CS 180 or 181, they're a very, very important category of problems with numerous applications in a bunch of fields, like everything from finance, cybersecurity, et cetera. Quantum computing is probably the best way to address these problems right now. And lastly, simulating quantum systems, one of the main applications for quantum computing, is very, very important and could allow for massive advancements in basically every natural science possible, physics, chemistry, biology, material science, they all want to be able to efficient quantum systems efficiently. And if we're able to do that, like, you guys all heard of like AI and like how they've been able to like see a bunch of like protein structures. Yeah, like that's like nothing compared to what quantum computing can do. Lastly, there's actually a lot of money involved in quantum computing. Governments around the world have invested roughly $55 billion already. And that's not even including the private sector like IBM, Google, Microsoft. Like they invested a crazy amount of money inside there. And secondly, quantum computing actually complements AI. There's a field called quantum machine learning that's just starting to take off. It's in its infancy, but it looks very, very promising. So AI and quantum computing actually like complement each other, and ChatGPT will help you keep your job. I'll hand it off to Arsh.
Thanks, Ian. I hope everyone is not scared about the gory details that we haven't even touched about quantum computers. But I would want to break down a quantum computer into different layers, just because it is a new way of computing. And you might see some parallels compared to a normal computer that is being used today. So let's dive deeper into what layers we have. All right, so this is what we call the quantum stack. So starting at the top, we have the quantum algorithm layer where we write some useful quantum algorithms like Shor's algorithm or Grover's algorithm, just like Ian mentioned. These get compiled into a quantum intermediate representation, or QIR. So think of it like an assembly layer that's portable across different hardware types. When I say different hardware types, I would want you guys to keep in mind that the current quantum computers are not based on the same hardware. Different companies are exploring different approaches to build a useful quantum computer. Below that, we have the logical qubits layer. These are basically virtual qubits built from many physical ones, made robust through error correction. So the instruction set architecture defines what operations we can do at these levels. Logical qubits are the actual useful qubits that are used for computation, unlike the physical qubits that we're going to just go over. So below the logical qubits layer, we have the quantum error correction layer. So this is key to useful quantum computing. It keeps qubits stable despite noise. Noise is something that is an interference from an outside environment. Since these are quantum systems, they're based on intrinsic natural properties that are very sensitive to outside disturbances. So using these kind of particles to perform useful computation requires us to minimize any kind of outside interference to minimize any errors. All right, so at the bottom, we have the physical qubits layer, the actual superconducting loops, trapped ions, all that good stuff, where companies are still exploring what is the best way to implement this. I've left a link at the bottom which explains this stack in more detail. We're going to share the slides with you guys after the presentation. All right, so who's building today's quantum computers? I'm sure you guys have heard of IBM, Google, Microsoft, but there are also some smaller companies like Rigetti, IonQ, D-Wave, and Continuum. All of these have different approaches to building a practical quantum computer. So IBM, Google, and Rigetti are focusing on something called superconducting qubits, where the actual quantum computing chip lives at the bottom of a fridge, which is cooled to a very low temperature, more coming later. Then we have the IonQ and Quantinuum. These two companies are focusing on another technology called trapped ions. D-Wave covers quantum annealing, which is one of the first few ways of implementing quantum systems. All right. Does anyone know what happened with Rigetti computing last year, or like end of last year, with the stock? No, okay. So fun fact, Rigetti computing stock was at $1.50, and it went up to like $16. And just saying, I made a lot of money there. All right. So covering the first technology of quantum computers, we have the superconducting qubits. This technology is being developed by IBM, Google, and Rigetti. So here we have the qubits that are stored right here at the bottom of the fridge. This is like one of the most like famous pictures that everyone sees of what a quantum computer looks like. But the entire computation just happens like in the small chip. This is all a big refrigerator, which is cooling the system to about 10 microkelvin. So qubits here are tunable frequency resonance circuits. So how you compute with a qubit is by tuning it to a specific frequency. So think of it like you're playing a guitar, but before playing the string, you got to tune it first. So in the superconducting environments, we use the ground state and the first excited state. So if you recall some chemistry classes, you would have an electron, and there's the normal state, which is the ground state, and the first excited state. That's what the theory is behind the 0 and the 1 that Ian covered in great detail, but from a mathematical standpoint.
So as I mentioned, the chip sits at the bottom of this fridge, which is highly cooled, and we send microwave signals or some form of waves from the outside to perform useful computation. So you would wonder why we do all this effort, why it's so cold. It is to avoid decoherence. Decoherence is something that we really don't want in the quantum world. It's really the noise that I mentioned, disturbances from the outside environment that can destroy any useful quantum information or computation that we perform. All right. And this is my favorite meme. All right, iron traps. This is the second most used or being worked on technology right now by IonQ and Quantinuum. Here, individual ions, which are charged atoms, are trapped using electromagnetic fields. So there exists a field in the middle, and we want to have the ions trapped there. So they float above the chip. They're not in physical touch or contact with any of the parts of the chip. These are just suspended above a chip using these electromagnetic fields, which makes them really clean and stable. We use precisely tuned lasers and microwaves to control them, flipping or entangling their quantum states. Think of it like flipping from a 0 to a 1. That is what the lasers are being used for. So because we're manipulating atoms directly, ion traps can achieve very high fidelity. By very high fidelity, I mean gates and operations that have very high accuracy and low error rates. So some of the most accurate quantum gates out there are based on this technology. However, they're slower than other types, and building a scalable version of the iron trap chip is extremely hard and an open problem right now. All right. Before I move on, does anyone have any questions about the two main technologies or the companies? So this section, we see what researchers are currently solving, some of the deep open problems that are out there. More reliable qubits. So currently qubits are very error prone and contain information. They cannot maintain information for very long. They're very sensitive to noise, and we would want to improve the technology of making these qubits in the first place. Exploring different options in qubit design. This is where all the material science engineering people come into play, where they're trying to explore what kind of different materials we can bring together to make this physical unit of computation. Most recently, Microsoft's Majorana 1 is claimed to be the breakthrough of implementing something called topological quantum computing. You can dive deeper into this using the previous link that was on the slide, but this is one of the most idealistic ways of building scalable quantum computers that are actually used in solving and implementing hard algorithms such as Shor's factoring algorithm. All right. The next open problem that we have right now is scaling up. So we need more qubits to do anything meaningful. Our current state is that for every one useful qubit computation, we need 1,000 qubits for error correction. If you remember the diagram I showed you guys above with the different layers, there was a layer which said logical qubits. So that is the layer where all the useful qubits sit, and we need a factor of 1,000 to from the physical layer clubbed with the error correction layer to actually make one useful qubit. And currently we have about 100 useful qubit quantum computers out there, but to achieve something like Shor's factoring algorithm that would break encryption in the world will break, I don't know, that will require about 1,000,000 qubits or so, order of 1,000,000. So how do we do this cost efficiently? That is one of the challenging problems. All right. Third, we have error correction. So correcting errors from the physical layer. We always have some amount of noise in our qubits that is inevitable. No natural environment is perfect. That is how the world around us exists. It exists in this disturbance that works perfectly.
And we would want to simulate that. That is what we're trying to achieve through quantum computers. So trying to recognize or correct errors when they occur. This is the most challenging part. Why do errors occur and how to correct them so that we have useful qubits? Think of it like a bit that has been flipped through some amount of radiation or heat, right? But we would want to have the idealistic world where it was all good before. So even one single bit flip, this is a classical version, but a single bit flip would result in this value being completely different from what we expect. Hence, just breaking all our computation. Our fourth and most important area, in my opinion, is to figure out what kind of problems are actually useful to be solved by a quantum computer. So I would want you guys to focus on this Venn diagram on the right. Researchers are hunting for problems where it is classically hard, extremely hard for like a classical computer to solve this problem, but it is easy in terms that it is faster and achievable to solve that problem using a quantum computer. So these are called quantum advantage problems. For the nth time, I would mention Shor's factoring algorithm because it is one of the key breakthroughs. And it has been proven to show that in an idealistic world, when we have a quantum computer, things like encryption will break. And that is not achievable by the current state of any most powerful supercomputers that are out there. Another example of this kind of quantum advantage problems is the simulation problem where we're trying to simulate the natural environment. We're trying to simulate how molecules and materials exist around us. And lastly, we have the optimization problem. So the real question is, what new real world problems can benefit from this upcoming technology? All right, so that brings us to the end of our first presentation, but I would want to leave you guys with what we have planned for next week. And this is where we're going to dive deeper into how quantum computers really work. And it is going to be a very math-focused section because we want you guys to know some of these concepts like linear algebra, complex numbers, probabilities, and the bracket notation. And this notation is derived from quantum physics that is being used in quantum computing as well. So with that, I would want to end our presentation. So it's about 6:50. We kind of ended early, but in the future, it is expected to take about an hour for every presentation. And yeah, I mean, if you guys have any questions, we're gonna stick around for a bit, just come up. But thank you for coming today, and we hope to see you guys in the future offerings. Thank you.